Okay. Hello, everybody.
Hi.
Good morning. So we're here today to present to you with a presentation on robot wiring. I'm Paul, and I'm from Team 1678.
And I'm Ellie. I'm a mentor that used to work with 1678, and now I'm with 5499. Okay, so when you're wiring an FRC robot, the most important thing is to know the basics of electrical engineering. And the basics come down to Ohm's Law, which is V equals IR, voltage equals current times resistance. So this is important because high resistance means that your robot is going to have to do more work to get electricity to all of your components. So do you think that a longer wire or a shorter wire will have more resistance in it? Anyone?
Longer.
Longer wire will have more resistance. What about a thicker wire or a thinner wire? Thinner wire will have more resistance. Thicker wire gets you more metal for electricity to pass through more easily. So when you have, first has requirements that wires going straight from the batteries have to be quite a lot thicker than wires going to, say, your sensors, right? That's because you want wires that are going to have less resistance, which means that they will generate less heat as current from your battery is going through them. So basically, to prevent your wires from melting and your whole robot from breaking down, you want to use thicker wires whenever you have a high current situation. So heat and power are closely related. Power is current times voltage, so that's related to Ohm's Law. As for capacitance and inductance, so inductance, you're not going to have to worry about too much in first, except to know that you create inductance, you create an electromagnet when you have a big loop of wire. So if you have a really long wire going to a motor and you don't feel like cutting it, and you make a big loop that goes all the way around all of the components in your robot, you're basically making an electromagnet with all of your electronics in the middle, and that's bad news. Things won't work, your sensors will break down. So in short, cut all of your wires to be as short as you can get away with. Capacitance, you're not going to have to worry about too much unless you're doing something fancy like making your own little circuit board. Then you want to know enough about capacitance to know when it's going to help smooth out voltages going into it, and when it's going to hurt you by making the reaction time of stuff coming into and out of that chip too slow. But with the basic first components, you're not going to have to worry about capacitance.
So basically, capacitors resist change in voltage. Okay, so for wiring a robot, what 1678 does, and what every team should do, is start with the block diagram. So the block diagram basically lays out all of the main components on the robot, which include the robo-reel, the power distribution board, the power pneumatics control module, the voltage regulator module, all those things, and lays them out according to power and then brains. So power would flow from the battery to the power distribution board, and from that on to everything that needs power, while brains would flow from the robo-reel to everything that needs signal or input signal into the robo-reel. The block diagram for FRC electrical is actually very similar from year to year, but organizing this diagram, which we will discuss later, is very different from year to year because of mechanical design, etc., the type of game.
So here's the 1678 power path from last year. So you start with the robot battery. All of your power goes through the main breaker so that there's an easy emergency shutoff. That will then go to the power distribution panel, which gives power to your relays, your speed controllers, your pneumatic control module, your robo-reel. The router gets to go through the voltage regulator module, which will take a wide range of voltages and output something that's very, very consistent. So say all of a sudden you gun it and your robot jumps forward really fast, you send all of your drivetrain motors running. if you've done this before, you'll notice that the voltage reading on the driver station will drop, right? When that drops, you do not want your router to go down, because then you will lose comms, you'll lose control of your robot for a while in your match. That's bad. The voltage regulator module will do a lot to help with that. So this is the beautiful CAD diagram that Paul put together this year to, this is all to scale. This is the Robo-Rio, that's the power distribution panel. These are speed controllers, motors. What else do we have here? The PCM, I think.
Voltage regulator module right there, and the pneumatics control module.
Yeah, and then Anderson connectors, which goes to the battery, and the
Main circuit breaker.
yeah, the main circuit breaker. So the reason they did this is to make it very easy to lay out components to scale and modify the layout over and over again without having to actually take all of the components up and rewire them.
So this is of course the power diagram, not the sensors. So here are the signal paths that we've laid out. We start with the Robo-Rio, which communicates with the router and the wireless bridge, so that the programmers can be able to control and talk to the Robo-Rio through the bridge. The Robo-Rio gets power from the power distribution panel, and also gets input from sensor input from sensors. The Robo-Rio then is able to control speed controllers or spec relays, communicate with the pneumatics control module in order to control pneumatics and solenoids, and through the speed controllers control motors as well.
So over the next few slides, we're going to break down what comes in your kit of parts into 3 categories. First is types of wires and connectors that you're going to find, then robot components, and then electrical tools that you use to actually assemble the robot.
So here are the basics wires and connectors. The small gauge wire that you use involves PWM, which is that black, red, and white wire that you see over there. Those are 3 conductor wires. The CAN wire, which is the green and yellow wires over there, and the Ethernet cable. So PWM is basically control that the Robo-Rio can use to tell your speed controllers what to do, and CAN can do the same purpose if you're using a CAN sort of system in order to control all of your speed controllers and devices. 6 gauge or greater wire, and 1678 uses 480 UG because the ones that we buy look very nice and have very nice curve ratios, curves. Are used for connecting the battery to the main circuit breaker, and then to the power distribution panel. We use that specifically because of what we mentioned earlier, the power and the resistance in making sure that our robot doesn't melt or fry. 12 to 18 gauge 2 conductor wires is used after the power distribution panel for connecting speed controllers to motors and such, because those wires are usually small and easy to route. Special Jackson cable as for bridge power, like the small gauge wire that you use to connect from your voltage regulator module to your bridge or your modem router into barrel connectors and other such connectors. You use electrical tape or heat shrink for insulation. Electrical tape may fall off, so heat shrink is often a good choice for creating permanent sorts of insulation. Solenoid cables also come inside the KOP. Crimps involve ring and spade connectors, also lug connectors, quick disconnects, which involve Anderson connectors, and narrow gauge connectors for the pin headers for connecting to the Robo-Rio. Finally, terminal blocks are useful for arranging your wires in a very neat fashion.
Okay, so these are the main main types of connectors that you're going to find in the kit of parts. So this is an example of a ring connector up at the top. A spade connector looks very similar, but doesn't connect all the way around. Those are useful. Connectors like this make connecting to sensors and anything that you want to be able to disconnect later without having just a solder connection. If there's something you expect might break, basically, if you can have crimp connectors instead of a solder joint, you probably want to do it. Anderson quick disconnectors, you'll see that that's what connects the speed controllers to motors. You use Anderson quick connectors there. And the bigger Anderson connectors are what you use with your battery. So that will go between your battery and the circuit breaker. Narrow gauge pins and pin headers are useful. This should look fairly similar, or this should look fairly familiar because this is basically a PWM wire with slightly different wire colors. If you want to plug different pins into your RoboRio, you're going to need to take a thin gauge wire and put a small pin on it. And these here are lugs that connect to gauge 6 wire. This is how you actually connect gauge 6 wire, which is what you connect to your battery, to the RoboRio, and to the power distribution panel.
Also, as a side note, the ring connectors right there are also used for the pneumatic switch, which we'll be talking about. So here's a list of the more general components. We've got the RoboRio right there for any new people here to FRC, speed controllers, and relays, the batteries, of course, the bridge, which the programmers use to connect to the robot, PCM, pneumatics control module, voltage regulator module, the main breaker, some other breakers and fuses which you plug into the power distribution panel, and your sensors.
Okay, these are the electrical tools you're going to need to assemble your robot. Crimpers. You're going to need to crimp all of those connectors. Wire cutters, wire strippers. This is a very fancy pair of wire strippers. If you can get a hold of a pair like this, you probably want to. Yes?
Where could I get a green clip thing like in the last picture, pulling down the other end?
Oh, they printed
This
out
was a 3D printed design. So there are actual board extension boards that you can get online. There's a lot of these are, you can talk to teams to find them, and also, yeah, they're online. All right.
So, yeah, email Paul later.
Yeah, email me. I'll have my email on this slide.
Soldering equipment, you don't need to get a fancy soldering gun, but you are going to need to solder on your robot. So buy like a $20 soldering iron, buy some solder, don't inhale the fumes. And then a heat gun you use to, once you have a solder joint, you want to make sure that it's isolated and insulated from any other wire and metal connector. You don't want it touching the chassis of your robot, for example, or any other metals. So heat shrink is probably the best solution. Electrical tape will work, and to use heat shrink, you need a heat gun.
Right. So you could also use a heat gun for any of those who are interested in working with PCBs. If you've got a printed circuit board that is heat resistant, when your pieces on it, like resistors and capacitors, are heat resistant, what you can do is set beads down on where you want your components to connect to your board. Put your components right on top and heat the whole board in order to connect them to the board properly. In industry, they actually use ovens that go up to this temperature of a soldering iron to very quickly make printed circuit boards. Alright, so laying out your robot is extremely important. Laying out the wiring, and even for mechanical and other purposes, it's really important to figure out how your robot will come together. So 1678 actually uses all of these methods, using paper models, drawing on whiteboards, and using CAD. We outline where the electrical components will go, where the wiring will go, and how it will not interfere with mechanical design, and how what we discussed earlier will not happen, like difficulties with resistance, power, magnetic fields, etc. It's also important to keep wires short, like power lines, in order to reduce resistance. And finally, because robots will break and electrical components will break as well, it's very important to be able to access all your sensors and all your parts in order to be able to easily get in, diagnose the problem maybe, and replace those parts so that you can get on in a competition. Alright, so here are the pneumatics paths, which are also important for electrical. We start with a compressor, which can be on the robot or off the robot, which then pressurizes tanks to 120 psi. It does this by a pressure switch, which determines electrically what the psi of those tanks are. The pressure switch then communicates with the robo-reel, and the robo-reel can then control whether or not the compressor is on or off. So at 120 psi, the robo-reel tells the compressor to turn off. Also, we can visually see the pressure in those tanks by a storage pressure gauge, which is just basically a bike pressure gauge. After the tanks, we have a pressure regulator, which releases pressure down to 60 psi and regulates psi past that to only 60. And that is our working pressure gauge that we work with for pistons, as regulated per the rules for FRC. This 60 psi goes to pneumatics, so manifold and solenoids to control pistons. Alright, so here are some important things to remember as an overview for anybody who came in a little bit later. So, the important connector types to know are terminal blocks, the quick disconnects, which involve the Anderson connectors, the pin headers and Molex connectors, which connect to the robo-reel and PWM connectors, the Wade-Muller connectors, which are basically just the power connectors for the robo-reel, the power distribution panel, the pneumatics control module, and the voltage regulator module, and scoop terminals, which are very much similar to those Wade-Muller connectors. It's important to attach your components to where you want them to go, and then wire exactly the length that you have them mechanically to be designed and for your robot to be able to move properly with those wires, and then cut the wire to its correct length and wire between those components. So avoid loose wires, but also avoid making your wires too short and adding a connector later on only to find that you can actually connect your wires properly. Make sure to avoid short circuits and make sure polarity is correct, so red connected to red and black obviously connected to black. Keep things adjustable, again, be able to be flexible when things break so that you can replace them, and label things. On both ends of wire, label things. If you unplug something and you test and you have no idea where it plugs back in, well then testing is not very important compared to how important labeling is. And finally, battery wiring is strictly regulated. The battery leads must be completely covered so that there are no shorts, there is no problems with connecting to pieces of metal on the robot that might cause sparking and melting of plastic or other components on the robot.
So I'm just going to reiterate a little bit of what Paul said on the last page. So we like to use what we call the pull test to make sure that all connections that we put onto the robot are strong enough to survive an FRC match. So give it a give every wire a pretty good yank. If it comes out, probably it wasn't seated well enough. If it can survive a pretty good yank, probably it won't come out during a match. Keep wires secure, and keeping them away from moving parts is easier said than done. You're going to have to take every moving part, do the full range of motion you expect on the robot, and see where wires end up. If they're in between two pieces of metal that are moving, if they're right next to a chain, if they're right next to a sharp bolt. you're gonna wanna zip tie them away from anything like that. Labeling things, as Paul said, very important. Keeping wires organized is gonna make your life so much easier when you're actually at competition, something goes wrong and you need to change it very, very quickly. And for pneumatic tubing, the same way you have a hose in your garden, you can put a kink in it and stop any water from getting out. You can do the same thing with pneumatic tubing and stop any air from getting to your solenoids and to your pistons. And that's a very bad thing. So even if you don't actually totally block the air pathway, you want to keep the curves in your tubing as gentle as possible so that you get the maximum amount of allowed pressure to all of your pneumatic systems.
Alright, so this is a completed robot. Of course, the presentation will be online for you guys to access afterwards. But basically this is a picture of each part. The legend for all of the wires are labeled, and this is basically a now modern robot in particular.
And Paul has a robot that he's been working on. They're going to be using it at Madtown Throwdown. In competition, if you guys want to come up and ask any questions about how it's wired, why it's set up the way it is, yeah, please come on up.
I know some of you guys have seen it before, but
Okay, question.
Why is it so small?
is this okay? It's so small for many different reasons. Firstly, because we decided it should be small because it would be a nice challenge to be able to fit such fit all of these mechanisms in. It would be difficult for the programmers to be able to program, so they'll receive a challenge. And it is very difficult to wire it because a lot of components are on the top swiveling part, so we have to direct everything to the center, go down, and connect everything at the bottom. So it's just practice, off-season practice. Other questions?
We're also happy to answer any questions about sensors, any aspect of electrical engineering, basically. So, yeah, that's what we have for you if you want to come up and look at it. And thank you very much.